So in the previous lecture we have learned about the condition for maximum work output. Okay, for maximum work output we have found out an expression called RP optimum. Okay, RP optimum means what? It is if we apply this pressure ratio. Okay, there we have given the pressure ratio, optimum pressure ratio in terms of maximum temperature and minimum temperature, and we all know that maximum temperature and minimum temperature is fixed from the before the design only, because the parts with which the components in the system are made with, okay, are going to resist some amount of temperature. Okay, and keeping that in mind, we are already fixing the T min and T max. Okay, so to get the maximum work output, what is the required or what is the optimum pressure ratio which we have found out in terms of maximum temperature and minimum temperature, and that was T max by T min to the power gamma minus 1, sorry, gamma by 2 into gamma minus 1. Okay, this was the optimum condition of pressure ratio. Okay, that means if someone asks you what if you want to take maximum work output from a Brayton cycle, what is the amount of pressure ratio you are going to get? This is the answer. Now we are going to find the conditions like temperature after compression and temperature after expansion. Okay, that means from 1 to 2 it is getting compressed, and from 3 to 4 it is getting expansion. Okay, so after expansion that is 0.4 and after compression that is 0.2. Okay, now we are going to find out if there is any condition with, that means to get the maximum work output, what should be the temperature T2 and what should be the temperature T4. Okay, these are the conditions which we are going to find for maximum work output. Okay, so first of all let us go for the temperature after compression. Okay, so 1 to 2 is again isentropic or adiabatic. Okay, for adiabatic this is the relation T2 by T1 Rp to the power gamma minus 1 by gamma. Okay, now T1 is what? T1 is the minimum temperature. Okay, so T2 is equal to what? T1 into Rp to the power gamma minus 1 by gamma. That means in place of T1 I have replaced it with T min. Okay, now for maximum W net. Maximum W net means what? What is the condition we know for maximum net work? For maximum network we know that Rp should be Rp optimum. Okay, the optimum value of pressure ratio is going to give us maximum W net. Okay, that means in this equation we are going to replace Rp by Rp optimum. Okay, so T2 is equal to what? T min into Rp optimum to the power gamma minus 1 by gamma. Okay, now T min into what is the value of optimum? Optimum value is this one. Okay, so within the above this there is going to be the power of this one. Okay, Rp value, okay, Rp optimum is going to hold this value. Okay, and this power is going to come above this value. Okay, now after that if you see what we will find, you will find that gamma gets cancelled out and gamma minus 1 and gamma minus 1 gets cancelled out. What is remaining? T max by T min to the power half. Okay, that means what? You are going to get T min into root over of T max by T min. Okay, root over of T max by T min you are going to get, because the power is going to be half. Okay, half power is nothing but a square root. Okay, so here is root T min, here is root 2 min. Okay, so if you simplify this, you are going to get root over T max into T min. Okay, that means for getting maximum W net, the value of T2 should be what? Root over T max by T min. This is another condition. Condition number 2. This is condition number 1. This is condition number 2. For getting maximum work output, T2 should be, okay, root over T max into T min. Okay, that means root over T3 into root over T1. Okay, this is going to give you the condition for max, that is the temperature after compression. Okay, so now we are going to find what should be the temperature after the expansion for maximum W net. Okay, now 3 to 4 is again an isentropic process, and from this we can write this relation T3 by T4 is going to be pressure ratio to the power gamma minus 1 by gamma. Okay, now from this T4 is what? T4 is nothing but T3 by Rp to the power gamma minus 1 by gamma. Okay, if you simplify this, you are going to get this. Now for maximum W net, Okay, maximum net work output, the RP should be having the value of R optimum. Okay, so in the next line we have directly put the value of R optimum in place of RP. Okay, so this is T max by T min to the power gamma by 2 into gamma minus 1 and whole to the power gamma minus 1 by gamma. Okay, now from this your gamma minus 1 and gamma minus 1 is going to get cancelled out, gamma and gamma is going to get cancelled out. Again the thing is, and T3 is what? T3 is nothing but T max. Okay, so you can directly write T3 is what? T max. Okay, so after this the T max will come here and T min will go up. Okay, that is root over T min. Okay, because the power is half. Okay, so root over T min divided by root over T max. So from this you are going to get root over T max into T min. Okay, that means what? The temperature after compression and temperature after expansion must be same. Okay, and that value is what? This is equal to T2 also. T2 equals to T4 equals to this one. Okay, that means the condition we are getting here is what? To get the maximum work output, the temperature after compression, that is T2, and temperature after expansion, that is T4, must have the value of root over T max into T min. Okay, that means these two temperature must be same. Okay, if you plot this in TS diagram, okay, these two temperature must be same, and T2 is equal to T4 is equal to what? Root over T1 into T3. Okay, root over T1 into T3. That is what? That is the geometric mean of the higher maximum temperature and minimum temperature is going to give you the optimum temperature which should be attained after compression and after expansion to get the maximum W net. Okay, so now we are going to see what would be the value of W max. Okay, if you go according to the conditions what we have achieved for getting the maximum W net. Okay, now if you put these conditions in the expression of W net, what is going to be the expression? Okay, that means what is going to be the formula to find out the maximum W net for a Brayton cycle, we are going to see now. Okay, now if you remember the W max, okay, or the maximum net work, the expression was like this. Okay, it had come from the difference of the enthalpies. Okay, in the last lecture, so it had come from the difference of the enthalpies. Okay, now in this place we have found for maximum W, we have found out the condition for T max and T4 and T2. Okay, so T4 and T2 both are going to be root over T1 dot T3, root over T1 dot T3, and T3 and T1 are going to be same. Okay, now T3, the term T3 we can rewrite it as root over T3 whole square. Okay, we can rewrite this T3 as root over T3 whole square. Okay, and if you add these, okay, if you add these, you are going to get minus of 2 into root over T1 into root over T3. Okay, this is minus T1 T3 minus T1 T3. So if you add this, you are going to get minus 2 into root over T1 dot root over T3. And you can again rewrite this T1 into root over T1 whole square. Okay, so root over T1 whole square is going to give you T1 again. Root over T3 whole square is going to give you T3 again. So if you see, this is going to be a formula of A square minus 2AB plus B square. Okay, A square minus 2AB plus B square, that is the formula of A minus B whole square. This is going to form a formula called A minus B whole square. Okay, so here A is what? A is nothing but root over T3 and B is what? Root over T1. Okay, so the final expression would be Cp. Okay, the final expression would be Cp into root over T3 minus root over T1 whole square. So if you put the maximum temperature value and minimum temperature value and Cp value for that particular medium which is running through the system, then you are going to get the maximum work output from a Brayton cycle. Okay, now we are going to see what is going to be the efficiency for maximum work output condition. Okay, so we have some conditions for maximum work output. If you put it in the formula of efficiency, you are going to get what is going to be the efficiency for maximum work output. So the formula goes like this: 1 minus 1 by rp to the power gamma minus 1 by gamma. Okay, and for maximum work output, the rp should be what? Rp should be rp optimum. Okay, and because it is rp optimum, that means the final, okay, the value of this is going to be tmax by tmin to the power gamma by 2 into gamma minus 1. Okay, in place of rp we are just putting rp optimum. Okay, and this value goes like this. Again, gamma minus 1 is going to get cancelled out, gamma and gamma is going to get cancelled out. Remaining thing is tmax by tmin to the power 1 half. Okay, that means the tmin will go to the denominator. Okay, so the final expression for efficiency, okay, that means efficiency for maximum work output is going to be 1 minus root over tmin by tmax. Okay, whole root over of tmin by tmax. Okay, now if a question is asked like this, that in a Brayton cycle, okay, the maximum temperature and minimum temperature is there. Okay, now to get the maximum, we have a condition for maximum work output. Now for maximum work output, what is going to be the efficiency? You directly put the value of maximum temperature and minimum temperature. The value you are going to get is going to be your efficiency for maximum work output. Okay, now we are going to see what are the optimum conditions we have found out till now. Okay, so the first thing we have got is the pressure ratio or the optimum pressure ratio. Okay, that means for work done to be maximum or net work output to be maximum, the optimum pressure ratio is going to be tmax by tmin to the power gamma minus 1 by gamma. Second thing we have found out is T2 is equal to T4 is equals to root over Tmax dot Tmin. That means what? The temperature after expansion and temperature after compression must have the same value. Must have the same value, and that value must be what? The geometric mean of maximum and minimum temperature. Okay, that means T2 and T4 should be that geometric mean of T3 and T1. Okay, now W max. W max we have found out it is nothing but Cp into root over T3 or maximum root over of maximum temperature minus root over of maximum temperature whole square. Okay, so this is going to be our net W max, okay, or maximum net work output which we are going to get. Okay, and the fourth one is the efficiency. Okay, to get maximum work output, the efficiency is nothing but 1 minus root over Tmin divided by root over Tmax. Okay, now we had given you the R optimum. Okay, now we are going to see how the W net is going to vary with respect to RP, okay, or the pressure ratio. Okay, so as if you can remember, we had said that for RP max W net was equal to 0. Okay, for RP max W net was equal to 0, and we had said that for RP max the cycle will be something like this. Okay, this will be T2 and the cycle will be in a straight line only. Okay, and if you remember, for RP mean also W net was equal to 0. Okay, and if you remember, that for RP mean, okay, for RP mean the cycle used to go like this and used to come like this. Okay, so for both the conditions W net was 0. That means if you take a minimum pressure ratio value and maximum pressure ratio value, at these 2 points the W net is going to be 0. Okay, and in between somewhere there is going to be a RP optimum. Okay, RP optimum is there in between these 2 points. Okay, so this is going to be what? RP mean, and this is going to be what? RP max. Okay, now if you draw a graph like this, in between this somewhere there will be a point which is going to be RP optimum. Okay, and at this optimum RP the W net is going to have the maximum value. Okay, otherwise at RP mean it is going to have 0 value, at RP max also it is going to have the 0 value. Okay, so these are the conditions which we have got or which we need to apply if we see the term like maximum work output. Okay, so now we are going to see some cases where certain irreversibilities are there. Okay, in Brayton cycle we know that all the processes are going to be reversible processes. Okay, but due to friction in some places we see that there are some irreversibilities. Okay, now this is the TS diagram for Brayton cycle. Okay, 1, 2, 3, 4 is going to form an ideal Brayton cycle. Ideal Brayton cycle. Okay, 1, 2, 3, and 4 is going to form an ideal Brayton cycle. Okay, but due to friction, sometimes what happens, this entropy increases. Okay, the entropy increases while passing through the compressor. Okay, now initially the entropy is constant. Now the entropy increases from S1 to S2 dash. Okay, that means entropy at point 2 dash is going to be higher than entropy at point 1. Okay, similarly for while passing through the turbine, then also the entropy increases due to the friction. Okay, now 1, 2 dash, 3, 4 dash, and 1. Okay, this is going to form an irreversible, okay, or actual Brayton cycle. Okay, the 1, 2, 3, 4 forms the reversible Brayton cycle, and 1, 2 dash, 3, 4 dash forms an actual Brayton cycle. Okay, now for this, if such conditions are given in the question, we need to find the isentropic efficiency. Okay, isentropic efficiency of the machines like compressor and turbine. Okay, so for compressor, the efficiency is going to, the isentropic efficiency is what? Whatever reversible work is given to the compressor is going to be less now. Okay, and whatever the work we need to overcome the friction, okay, whatever the work we need to overcome the friction as well as to run the friction is going to be higher now. Okay, this work is going to be higher and this work is going to be lower. Okay, that means for turbine compressor, what happens, this efficiency is going to be the ratio of reversible work, which is less. Reversible work divided by actual work which you need to get. Whereas in turbine, what happens, this is actual by reversible, because actually the temperature difference is now small. Okay, in actual case, so this is going to be in the numerator. Okay, and in the reversible process, we have seen that we could have got this much amount of work. Okay, work which is where the temperature difference of this much, that much work we could have got, but due to the friction, now the work we are getting is of this small temperature difference. Okay, so in both the cases, W reversible means what? This is the reversible part. Okay, for compressor, so this is going to be W2 minus W1. H2 minus H1. This is the enthalpy difference. For compressor, the work is what? Enthalpy difference. Okay, and actual work is what? H2 minus H1. Okay, now if you remember, these values are going to be Cp into T2 minus T1. Okay, for H2 the value is Cp into T2, for H1 the value is Cp into T1. We are taking Cp common, the remaining thing is T2 minus T1. Okay, in the denominator again Cp is common, the remaining thing is T2 dash minus T1. Okay, that means the final isentropic efficiency of the compressor is what? T2 minus T1 divided by T2 dash minus T1. Okay, now this is going to be the isentropic efficiency for compressor. Coming to the turbine, the isentropic efficiency, this is the similar thing. Okay, actual is what? Actual is 3 to 4 dash. Okay, so H3 minus H4 dash and H3 minus H4 is the reversible thing. H3 minus H4 is the reversible thing. Okay, so again like this Cp we are taking common, then T3 minus T4 dash, T3 minus T4. Okay, the ratio of this is going to give you the isentropic efficiency of turbine. Okay, so now we are going to see a free shaft turbine. Okay, it is a special type of turbine. Okay, what happens, the air goes into the compressor. After getting compressed, okay, it passes through the combustion chamber, that is it gets heated. Okay, after that it passes through the high pressure turbine. Okay, that means the high temperature and high pressure air which is coming out is going to pass through the high pressure turbine. That means in high pressure turbine, the high pressure air which is coming into the turbine is expanded to a relatively low pressure air. Okay, but not low pressure. Okay, then whatever the relatively low pressure is there, low pressure air is there, is again passed to the low pressure turbine. Okay, and from that turbine the work generation takes place. Okay, and whatever the work is done by the high pressure turbine is used to run the compressor. Okay, That means whatever the small amount of work that is received from this HPT or high pressure turbine is going to be used to run the compressor. Okay, and whatever the remaining pressure ratio is there is going to help us to get the work W generation. Okay, the amount of work we are going to get is from the low pressure turbine in this thing. Okay, now this is the TS diagram. In TS diagram, what happens? This is the 1 to 2 is going to be compression, 3 to 4. Okay, so this is the work given to the compressor. Okay, through this 3 to 4 is what? From 3 to 4 we are getting WHPT. Okay, from 3 to P we are getting WHPT. Okay, and from 4 to 5 we are getting WLPT. Okay, so this is the amount of work we are going to receive. Okay, we are going to receive this much amount of work, and this much amount of work is used to run the compressor. That means from there we can say that WC must be equal to the WHPT. Okay, because this runs the compressor. Okay, so from this WC is what? Nothing but the temperature difference of enthalpy difference of the compressor. Okay, enthalpy difference of the compressor, and this is nothing but the enthalpy difference of the higher pressure turbine. Okay, or high pressure turbine. So since temperature difference is nothing but there is a Cp into temperature difference. Okay, so since Cp is going to be same, so Cp is going to get cancelled out from both the sides. The remaining thing would be T2 minus T1 is going to be equal to T3 minus T4. Okay, again if you see that means what is going to be the W generation. Okay, that means what amount of work we are going to get, it is nothing but the enthalpy difference in this portion. From 4 to 5, what is going to be the enthalpy difference there? That means the enthalpy difference from the low pressure turbine is going to be our W generation. Okay, so it is what? Nothing but Cp into T4 higher temperature minus the lower temperature. Again, pressure ratio is going to be same for this case and this case. Okay, since we have said that both of them are constant pressure. Okay, so it is going to be P2 by P1 is going to be equal to P3 by P5, and P3 by P5 we can rewrite it as P3 by P4 into P4 by P5. Okay, P4 and P4 will get cancelled out, so again P3 by P5 will be remaining. Okay, so P3 by P4 is what? P3 by P4 is nothing but the pressure ratio of high pressure turbine. Okay, and P4 by P5 is nothing but the pressure ratio of the low pressure turbine. Okay, so pressure ratio in such case is going to be high pressure ratio of high pressure turbine multiplied by pressure ratio of low pressure turbine. Okay, now we are going to read about the analysis of combustion chamber. Okay, now in analysis of combustion chamber we have read about two types of there are two types of combustion chambers. Okay, one is open system combustion chamber and one is closed system combustion chamber. Okay, now while reading the Brayton cycle we have read about two types of Brayton cycle. One is open system Brayton cycle and another one is closed system Brayton cycle. Okay, now in open system Brayton cycle, what used to happen? The compressor used to take the air from the atmosphere. Okay, and after that, while it is compressing in the compressor, the temperature and pressure of that air was rising. Okay, and while it is reaching to the combustion chamber, we used to inject the fuel into the combustion chamber. Okay, now as the temperature of the air, okay, the temperature of the air is higher than the self ignition temperature of that mass of fuel. Okay, or that fuel. Okay, whatever is the self ignition temperature of that fuel, the temperature of air which has been compressed through the compressor and coming to the combustion chamber had the temperature which is higher than the self ignition temperature of that particular fuel. Okay, so in that moment when you are injecting that fuel, that fuel used to ignite itself. Okay, that means in combustion chamber what used to happen, the air also is coming in and the fuel also is coming in. Okay, now after that combustion is happening, then temperature is further rising, then whatever the products is coming out of the combustion chamber is expanded through the turbine and the remaining air, okay, or the exhaust air which is released into the atmosphere again. Now in the combustion chamber what is going to happen, once you are giving the air, fuel is also coming. Okay, so fuel is also coming into the combustion chamber, makes it an open system combustion chamber, and this open system chamber combustion chamber is generally used in open system Brayton cycle. Okay, so if this is the combustion chamber, here we had a compressor, and after coming out from there we had a turbine here. Okay, so as the mass of air, this is going inside this combustion chamber. Okay, after going to this, the mass of fuel, okay, mf means the mass of fuel. Okay, an amount of fuel is injected into the combustion chamber, and as a result, whatever the mass of fuel is injected and whatever the air is going to come into the combustion chamber was mixing, then the final amount of mass which is been coming out of the exhaust gas must be the mixture of, okay, or the summation of whatever the air is coming in and whatever the mass is coming in, that together comprises the mass that is coming out of the combustion chamber. Okay, now after that, if we go for an energy balance, okay, energy balance, what is going to happen, we will find out whatever the energy, whatever energy the air or whatever matter is going into the system, okay, as inlet must be equal to the energy of whatever substance is coming out of the system. Okay, that means if you are giving in air, okay, with what energy that air is going into the chamber, and if you are giving the mass of fuel, with what amount of energy it is going to contribute into this combustion chamber. Okay, these two will comprise whatever the energy is going to come out as an exit, okay, or the exit product of that combustion chamber must be same. Okay, then these two is going to give us our energy balance. So first thing is what? First thing is whatever the mass of air is coming with, coming in the energy with. Okay, that means the mass which is coming in, with what energy it is coming in, it is coming in, that means the mass of air is there, and Cp into T2, that means we are finding out what is the enthalpy of the air that is going into the combustion chamber. Then what is the enthalpy? It is nothing but mass of air into Cp into the T2. Why it is going to be T2? Because we have said that here there was a compressor, okay, that was 0.1 and that was 0.2. That means what? After, before going into the compressor, that was 0.1. Okay, if you look at the PV diagram also, this was like this. Okay, so before the compression was there, this was 0.1. After the compression, it was 0.1. 0.2 to 0.3 was heat addition. Okay, in PV diagram. Okay, similarly here, what is going to be there after compression? It is going to attain a temperature. Okay, it is going to attain a higher temperature than 1, which is going to be nothing but T2. So that's why we are writing T2 here. Plus, what is the amount of energy that is given by a certain amount of mass? Every fuel has a calorific value. Okay, every fuel has a calorific value. It is a factor to determine whatever the energy it is going to give in. Okay, now if we multiply that calorific value with the mass or the mass of the fuel, okay, that is the calorific value multiplied by the mass of the fuel is going to give you the amount of heat that is the fuel is going to contribute for energy generation. Okay, so for the energy balance, whatever the energy the fuel is going to give, it is nothing but mass of the fuel into calorific value, and we are multiplying one efficiency of combustion. Okay, that means at what amount of the total heat is going to be collected. Okay, that is going to be given by the efficiency of combustion. Okay, that is eta C, equal to what? Equal to what? With whatever enthalpy the product is going to come out. What is the enthalpy here? Mass. The total mass that is coming out is mass of air plus mass of fuel. Okay, and the Cp exit. Okay, Cp suffix E, that means whatever. Now this is going to be a different air or different fluid altogether. Now there the Cp value is going to change. Okay, there one fluid was coming, one fluid is coming down. Now mixing that, another fluid is coming. Okay, now after this Cp is going to be the Cp of the exit air. Okay, and the temperature of that must be T3, because from 2 to 3 is heat addition. So before, after the combustion is done, the temperature it is going to attain is going to be T3. So this is going to be our T3. Now what we can do, we can divide this equation with the mass of fuel. Okay, now if we divide this whole equation with mass of fuel, what is going to happen? This is nothing but Ma divided by Mf. Okay, Cp into T2. Okay, plus MF is going to get cancelled out. So what is remaining? CV into CV. This CV is nothing, not the this CV is not the specific heat at constant volume. This is calorific value. Okay. Now what is going to happen here? This is nothing but MA plus MM divided by MF CPE into P3. Okay. Now this is going to be there. Now after that, if you remember what is going to be the air-fuel ratio, air-fuel ratio is nothing but mass of the total air divided by mass of the total fuel is going to give us the air-fuel ratio. Okay, this is going to give us the air-fuel ratio, mass of air divided by mass of fuel. So from this you can write what you can write, MA by MF is nothing but air-fuel ratio. Okay, air-fuel ratio Cp into T2 plus Cv into eta C. Now here what you can do, MA by MF is going to give us air-fuel ratio and MF by MF is going to give us 1. Okay, so here you can write air-fuel ratio plus 1 Cp at exit into T3. Okay, so this is going to be the energy balance equation for open system combustion chamber. Okay, this is going to be the combustion chamber energy balance equation. Now from here, if the Cp at exit is given, Cp of air you already know, temperature are given, and they are asking you to find what is going to be the air-fuel ratio. Now you can easily find it from this equation. Okay, so in this way we can analyze the open system combustion chamber. Okay. Okay, so now we are going to look for our closed system combustion chamber. Closed system combustion chamber, what is going to be there? The procedure is completely same, but in closed system closed Brayton cycle, what used to happen, the same air used to circulate inside the systems, okay, to form different cycles. Okay, that means only the single amount of mass of air which has been inserted into the systems, okay, that amount of mass is going to circulate only, okay, inside that total system of Brayton cycle. Okay, now the air injection is not going to take place inside the closed system Brayton cycle. Okay, now the fuel injection is not going to be there. That means what? The mass of air that is going to be constant. Previously what used to happen, in the air we used to inject the fuel. Okay, we used to inject the fuel and the air fuel mixture used to come out through the turbine. Okay, now in closed Brayton cycle the fuel injection is not going to be there. That means only the mass of air is going to pass through the combustion chamber, and only that amount of mass is going to be passed through the turbine. Okay, now how does the heat addition take place in Brayton cycle? The heat addition takes place by combusting the fuel outside the this heat exchanger. Okay, outside there, the combustion chamber is outside the system. Okay, only this is combustion chamber, only the heat used to come. Okay, only the heat used to come to heat up the compressed air. Okay, the compressed air is coming through here. After passing through the compressed air is coming. Only the heat used to come inside the system to rise up the temperature of that air, and the same amount of previously mass of air plus mass of fuel used to come out. Now only the mass of air will come out, since we are not injecting any fuel. Now if you go for the energy balance, what is going to be there? Mass of air into Cp into T2. This is going to be the enthalpy at inlet. Okay, this is going to be the enthalpy at inlet. Mass, what amount of heat is going to come? The amount of heat which is going to come for that open cycle or open system combustion chamber and the closed system combustion chamber is going to be same only. That is mass of fuel into calorific value into combustion efficiency. Okay, and what is going to be at energy at the exit? Energy at the exit is nothing but whatever the air is coming out, okay, multiplied by Cp. Okay, the Cp value is going to be same now. Okay, for air, for inlet and exit, the Cp value is going to be same, because the mass or the substance that is coming in and coming out are same. Previously it used to come in as air, used to go out as air fuel mixture. Now since the same thing is passing, Cp is going to be constant and the temperature attained is nothing but T3. Now again, if we divide all these things by mass of fuel, what is going to be there? This is going to be mass of, now mass of air is there, mass of, if we divide it by mass of fuel, what is going to be there? This is going to be a air fuel ratio. Air fuel ratio Cp into T2 plus here If you divide it by mass of fuel, what is going to be there? Cv into eta C. And here also, if you divide by mass of fuel, what is going to be there? This is going to be nothing but AFR, or air fuel ratio, into Cp into T3. Okay. Now this is going to be our energy balance equation for closed system. Okay, for closed system combustion chamber. Okay, again now if you are asked to find the air fuel ratio from the closed system combustion chamber, temperature T3 and T2 are given, calorific value is given, this efficiency of combustion is given. If it is not given, always consider this as 1. Okay, sometimes in question efficiency of combustion is not given, so you are going to take it as 1. Okay, now taking this 1, all the value Cp of air, you must remember always what is going to be the Cp of air, that is 1.005 kilojoule per kg Kelvin. Okay, so all the values will be known now. You are asked to find the air fuel ratio, you can easily find out. Okay, so this was our analysis for closed system combustion chamber. Now we are going to see what is going to be the mean temperature of heat addition. Okay, mean temperature of heat addition means what? At what or at what constant temperature, if you give the heat, that total amount of heat is going to be same as that of the actual process. Okay, now that means what? Now suppose there is a process going from 1 to 2. There is a process going from 1 to 2. Okay, so how can we find out what is going to? It is in TS diagram. Okay, it is in TS diagram. Now how can we find out what is going to be the amount of heat that is given in as input, okay, into this process? Okay, that means while completing this process, while it is moving from point 1 to point 2, or state 1 to state 2, what is going to be the amount of heat? It is nothing but whatever the area it is going to cover while it is projected on the entropy axis, then whatever the area it is going to cover is going to give you the amount of heat. Okay, amount of heat as input. Now we need to find a mean temperature. Mean temperature means what? A temperature, okay, in between these two temperatures that must be having a constant value. Now, okay, that means mean temperature of heat addition means what? Whatever the heat you are going to give in this process 1 to 2, okay, now we want to find out what should be the constant temperature at which we must give heat such that that amount of heat is going to be same as that of this amount of heat. Okay, now let us suppose we are marking a constant temperature line here. Okay, in such a manner we are going to choose this line. Okay, in such a manner such that the area, okay, such that the area which is covered by this line, okay, such that the area that is covered by this line is going to be same as that of area covered by the process 1 to 2. Suppose this is 1 dash and this is going to be our 2 dash. Okay, so that means what? Blue area must be same as that of black area. Okay, that means what? Whatever the heat you are going to give in the blue area, okay, is going to be equal to the total amount of heat which is denoted by the black area. Okay, that means the area of the blue part and area of the black part is going to be same. Okay, now for them to be same, the blue area and black area same means what? Whatever the heat input is going to be there in the process 1 to 2, the same thing would be, the same amount of heat would be given in process 1 dash to 2 dash. Okay, now for this to be same, for the heat to be same, okay, the area must be same, and that temperature, that constant temperature at which the heat must be given such that the amount of heat that is given at constant temperature Tm is equal to the amount of heat given from process 1 to 2 is nothing but the mean temperature of heat addition. Okay, now this concept is known as the mean temperature of heat addition. Okay, now this is required in most of the cases. Now if you see in Carnot cycle, what is there in Carnot cycle? If you draw the TS diagram, okay, if you draw the TS diagram, the Carnot cycle is nothing but like a square or rectangle in the TS diagram. If this is a TS diagram, this is going to be a Carnot cycle. Okay, sorry, this is the reverse Carnot cycle. the Carnot cycle would be like this: 1, 2, 3 and 4. So this is the Carnot cycle. Now for a machine, what is there? The maximum temperature is always fixed. Okay, the maximum temperature is always fixed. Okay, that cannot be changed, because we need to find out a maximum temperature up to which a machine can tolerate. Okay, now for this reason the maximum temperature is always fixed. Now suppose it is going to be the heat addition process for a Brayton cycle or any other cycle. Let us suppose it is for Brayton cycle. So let us take that T2 is maximum. Okay, and they have said that we cannot go beyond 300 Kelvin. Let us say this is a value which we are taking. Okay, so let us take that the maximum temperature any cycle can give is going to be nothing but 300 Kelvin. Okay, so if you apply in the same process, if you are going to run through a Carnot cycle, there also here also you are going to take T2 equals to T3 equals to 300 Kelvin. Okay, since the maximum temperature, the process does not matter. Okay, or the process you want to take, whatever process you want to take is going to be there. Okay, is up to you. Okay, now maximum temperature for any other cycle is 300 Kelvin. Here also 300 Kelvin. Now what is happening in any other cycle? The mean temperature is going to come down from the maximum temperature. That means for all other cycle, maximum temperature is greater than the mean temperature. Okay, mean temperature of heat addition. But in Carnot cycle, what is there? The heat addition process is constant temperature process only. Okay, so this is the T mean. This is the T mean. T mean. This is the T mean for Carnot cycle. That is the mean temperature for heat addition for Carnot cycle is equal to the maximum temperature also. This is the maximum temperature and this is also the mean temperature. Okay, that means for Carnot cycle T max is going to be equal to T mean. Okay, but for any other cycle the value of T mean, okay, or the mean temperature of heat addition is going to come down than the maximum temperature. That is the reason why Carnot cycle is going to have the maximum efficiency than all other cycles. Compared to all other cycles, the Carnot efficiency is going to be maximum, because it can give the maximum mean temperature of heat addition. No other cycle can give maximum. This is T mean. Okay, only this T mean will come here only when T1, okay, or the point 1 will come here. This only happens in Carnot cycle. So Carnot cycle is going to have the maximum amount of mean temperature, and that is the reason the efficiency of Carnot cycle is always greater than all other cycles. Now we are going to look at the history of our IC engine. Okay, we have completed the air standards. In the air standard cycle, we have completed the Brayton cycle. Okay, the remaining two cycles are Otto cycle and diesel cycle and dual cycles. Okay, and in all these things falls under the IC engine also. So we are going to look at the history of IC engine. Okay, so at first in the 17th century, okay, that is at 1680, Christian Huygens has given us a theory, okay, or given us a machine which used to run on a fuel called gunpowder. Okay, fuel called gunpowder. That means he used to give gunpowder as fuel. He used to ignite that gunpowder, and due to expansion of this, the piston used to come out. Okay, and the piston used to come out and used to give us the work. Okay, so in 17th century, this was the concept of our IC engine. Okay, that in IC engine means what? Internal combustion engine. The gunpowder used to ignite inside the cylinder only. Okay, and due to the temperature and pressure of the air which was situated inside the cylinder other than the gunpowder used to rise up. Okay, temperature, volume used to rise, and pressure also used to rise up, and for this we used to get a work output. Okay, so in this way the 17th century IC engine, the first IC engine, was developed. In 19th century, that is in 1816, the second attempt was made by Mr. J.J. Lanier. Okay, so in his machine, what he used to do, from 0 to 1, okay, that means half of the stroke. Okay, half of the stroke used to what? The suction. Okay, that means what? Up to when the piston comes to half of this cylinder, it used to a vacuum used to be there inside the cylinder. A vacuum used to be there. Okay, so for this vacuum, okay, 0 to 1 is what? 0 to 1 is nothing but suction. Okay, so at zero position, the cylinder is having a clearance volume. Okay, this is the clearance volume. Okay, this is the clearance volume. So at up to half, okay, up to half, that is at point 1. At point 1 it used to come. Okay, so due to this movement of the piston inside this, a vacuum used to generate, okay, or develop. A vacuum pressure used to develop. That means what? Due to this vacuum, the air fuel mixture used to come inside the cylinder. Okay, that means up to this volume, okay, up to this volume, air fuel mixture was filled. Then after that, without any compression, they used to burn this air fuel mixture or ignite this air fuel mixture. Okay, that means what? Keeping the volume constant. That means from 1 to 2 is going to be what? Nothing but constant volume process. Keeping the volume constant, heat addition is going to be there. Okay, heat addition takes place. Okay, at constant volume. Now after that, while it is at point 1, it goes to point 3. Okay, it goes to point 3. This is point 1 and point 2 also you can take, because 1 and 2 take place at the same volume. From 2 to 3, what? The 2 to 3 is nothing but it is an adiabatic expansion. Adiabatic expansion, that is Pv to the power gamma is equals to constant. Okay, so this used to be our linear cycle. Okay, so according to him, this was the condition. This was the cylinder. Up to half of his stroke, it used to suck in the air or air fuel mixture. After that, keeping the volume constant, they used to ignite the air fuel mixture, and after, due to the ignition, the pressure and temperature of this is going to increase. Similarly, volume is also going to increase. So that is the reason 2 to 3 is going to be our expansion, and after that again 3 to 0 is going to be our exhaust stroke. After reaching 3 to 0 is again going to be our exhaust stroke. So again the cycle will start from 0. Now if you consider the efficiency is nothing but what? 1 minus Q rejected by Q input. Okay, this is our Q input and this is our Q rejection. This is a constant volume process, this is a constant pressure process. Okay, so from this you can easily write that 1 minus QR is what? What is QR? QR is nothing but M into Cp into T3 minus T1. Okay, this is going to be our Q rejected, and what is going to be Q in? Q in is nothing but M into CV because it is constant volume, T2 minus T1. Okay, now the representation of the PV diagram, okay, representation of PV diagram according to the cylinder and according to the cycles is going to be explained well in the Otto cycle and diesel cycle. Okay, now in this lecture we are simply showing you what is going to be our efficiency for linear cycle. Okay, now we are roughly saying the main explanation would be started in Otto cycle. Okay, how the clearance volume is represented in PV diagram, how the swept volume is going to be represented in PV diagram, how the efficiencies are going to act. Like this, all the things will be explained well in Otto cycle. Now we are just reading the history. Okay, so in the third attempt, Nicholas Otto developed a 4-stroke SI engine. SI engine is nothing but spark ignition engine. Okay, so Nicholas Otto in 1876, again in 19th century, that means in 1878, Nicholas Otto has developed one 4-stroke engine in which we do spark ignition. Okay, or spark ignition engine. Okay, that means we provide a spark so that the air fuel mixture inside the cylinder gets ignited. Okay, and 2 years later, in 1878, Mr. D. Clark has developed a 2-stroke engine. Okay, now most of people think that 2-stroke engine has been developed earlier than the 4-stroke engine. Now 2-stroke engine has been developed 2 years later than that of the 4-stroke engine. Okay, that means the Otto cycle. After the 4-stroke Otto cycle or Otto engine, 2 years later the 2-stroke engine has been developed. Now in Mr. Atkinson in 1882. Okay, this was in 76, 72 and this one in 82. He has again developed a 4-stroke engine, And here Nicholas Otto has developed also a one 4-stroke engine. But what is the difference? Atkinson has developed one 4-stroke engine which has the expansion ratio greater than that of compression ratio. Okay, now this is a PV diagram. Okay, now this point, okay, 1, 2, 3 and 4 represents an Otto cycle. Okay, we'll see this in detail, but for now you are going to learn this. Okay, we are going to say briefly what is Otto cycle. Okay, now 1, 2, 3, 4 consists of an Otto cycle. Okay, now in Atkinson cycle, what he has done, he has the 3 to 4 is nothing but expansion process. Okay, that means a power stroke. Okay, expansion in the cylinder is always recognized as power stroke. Now 3 to 4 is expansion stroke. Now in Atkinson cycle, what he has done, he has increased the expansion. Okay, expansion stroke he has increased up to the initial pressure. Okay, it has started from this pressure. Okay, now he has ended the expansion in the same pressure as that of the beginning. But in Otto cycle, we start from point 1. Okay, and the expansion process ends at a pressure slightly higher than the initial one. This is the initial one and this is going to be the final one. Okay, final one means after expansion what is going to be the final state. So in Otto cycle, the expansion stroke ends at a pressure slightly higher than that of the pressure in the cylinder initially. Okay, but in Atkinson, what he has done, Mr. Atkinson has expanded or extended this expansion up to a pressure which is same as that of the previous one. Okay, so this was the special thing about the Atkinson. Okay, or 1882. In 1892, what has been done? Rudolf Diesel has developed compression ignition engine. Okay, CI engine is what? CI engine is nothing but compression ignition engine. In compression ignition engine, what is done? We do not. There is no spark ignition. Okay, there is no spark ignition. That means what? We compress the air inside that cylinder in a so much higher level. Okay, that means the initial volume and the final volume difference is very much higher. Okay, that means we are compressing it in a such a high manner or in such a manner that its temperature and pressure automatically gets increases. Okay, and since its temperature increases, the air fuel mixture which is present inside the cylinder, okay, they have a certain self ignition temperature. Self ignition temperature means what? If we reach that temperature, then the certain things will ignite or combust by themselves only. Okay, suppose there is an air molecule. Okay, its self ignition temperature is 300 Kelvin. Okay, now if we release this to a temperature of 400 Kelvin, it will automatically ignite, because the ignition temperature of this or self ignition temperature of this air is going to be higher than this temperature is going to be higher than that of the self ignition temperature of this particular air. Now if you release it to the surrounding of a temperature higher than its self ignition temperature, then it is going to be automatically combust or burnt. Okay, that means in diesel cycle we do that. We create a temperature higher than the atmospheric self ignition temperature of that particular air fuel mixture, and once that certain temperature is reached, the air fuel mixture which is present inside the cylinder ignites itself. So this is a compression ignition engine. Now if you see the first IC engine has been developed in 17th century. Okay, but all the attempts that has been done, okay, and the final or the engines we have right now has been developed in the 19th century itself. Okay, till the 19th century all of the engines have developed themselves. In the next lecture we are going to see the Otto cycle in details. Okay, and not only that, we are going to see how we represent the volume and pressure in PV diagram considering a certain state of the Otto cycle. Okay, that means if you consider certain cylinder positions, okay, then what positions are going to be represented in what place of the PV diagram we are going to see in details. Okay, so in next lecture we are going to start Otto cycle.